All right. Hope this is recording. Hello, TA and Professor. My name is Francis Walsh, and I'm just going to walk you through the presentation for 6810 Power Electronics. So, my project was the design, simulation, and PCB design of a lithium-ion battery charging circuit for an underwater AUV. So just a little outline of the presentation. We're going to start off with an introduction about battery management systems, or BMSs, the context of the application for the charging circuit that I've designed, as well as talking about some design decisions that I omitted from this project since they're out of scope. We're also going to do literature review, just looking at other researchers who have developed low form factor lithium ion charging circuits and using those to benchmark our design. Then there's a mathematical analysis. So the mathematical analysis was using the common design equations to select the passive and active components. Then the circuit was simulated, and we're just going over that. Going to talk a little bit about the PCB layout, just a little extras because this is a project that I work on in my own time, and then some conclusions. So just to preface this, this presentation is just a brief overview of the paper, which goes far more in depth. So we're not going to deal with any of like the math-heavy equations or anything. So what is a battery management system? So a battery management system basically has two very important functions, and that is charging and protection. Now the protection is a little out of scope for this project, so we're just looking at the charging portion of the battery management system. So lithium-ion cells follow a very specific charging profile. You can see that on the left here. So basically, as the cells charge from 0 to 100% state of charge, or SOC, their voltage goes from 3.2 volts to 4.2 volts. But in order, so a lithium-ion cell, as you can see right here, is actually just a chemical reaction held into a metal cylinder. So depending on how much electricity, current, voltage that you put across the cells, could actually really upset them, damage the lifetime, the longevity of the cells, or could even lead to fire. So you need to make sure that you're following this lithium charging profile pretty specifically. There's 3 stages of charging. So cell float. So that's right in the beginning when the cells are near 0% SOC. They're trickle charged at about, I think it's about 100 milliamps. And that's just to get the plating on the cathode and the anode to re-anodize inside the cell, so the cathode and the anode. And then constant current phase, so that's where the bulk of the energy is put into the cells. So that's also known as the fast charge phase. And so that takes the cells from about 10% SOC all the way up to 80% SOC. And then finally, there's the voltage controlled charging phase, and that's where the battery is gently, or the cell is gently charged from 80% to 100% SOC. So that's usually from about your 80% to your 100% point of state of charge. And then finally, I just put in a picture of what a commercial battery management system looks like. So on the bottom there, that's the Orion 2 battery management system that we used with Paradigm Hyperloop for our 800 volt lithium ion DC battery. So that could also be installed in electric vehicles, as they are very commonly. And just wanted to put that there as a reference. And so finally, the last slide of the introduction, we're just going to go over the applications context. So basically, this charging circuit, this lithium-ion battery management system, and the charging circuit will all go onto this PCB down here in the right corner. And that PCB actually goes inside into this electronic stack up you can see here. That's the middle board with the lithium-ion cells and the cell holders. And then that goes inside this underwater autonomous unmanned vehicle that we're designing for my senior capstone project. And so these electronics go inside a hermetically sealed enclosure. And so that really causes two huge constraints. So that is that space is limited. So any increase in any of the dimensions exponentially increases the size of the hermetically sealed enclosure. So the size has to be kept very, very small. As well, the ambient temperatures are really high since there's only a small volume of air used for convection and conduction cooling, and that's carried out to the edges of the board, so or the enclosure. And so efficiency of the circuit is also very, very important because it has to be the efficiency has to be very high so that the components do not overheat and ultimately fail or get stressed. So, and then the very final thing, so one of the designs of the buck controller, of the buck converter that was kind of out of the scope of this project was just talking about the charge controller. So the charge controller was selected to be a BQ24610 standalone lithium ion charger. And this was selected due to a multitude of systems reasons, which really didn't concern the design of the buck converter. And so all that we really need to know about it is that it's a fixed 600 kilohertz switching frequency, and it has two NMOS gate drivers, so one for the low side, one for the high side. So it's also bootstrapped, and that also means that it's a synchronous buck converter. It also has a pre-programmed lithium-ion charge profile, so we don't need to worry about doing any lookup tables or anything in an analog or digital control system. And finally, there's gate driver outputs for power path selection. And so that just comes later in the simulation. And then finally, the cell configuration that was selected for the whole underwater autonomous electric vehicle was 3 cells in series and 8 cells in parallel. And so what we can take from that is that at 0% SOC, the battery has a charge voltage of 9.6 volts. At 100% state of charge, the battery has a 12.6 volt voltage. The battery is capable of holding 20 amp hours, which is pretty close to a car battery. It has a maximum continuous current of 80 amps when it's discharging. But when it's charging, the current is maximum 8 amps into the battery terminals. Cool. So now we're just going to take a look at some literature review and just look at how I benchmark this system. So basically, the main thing, as I said before, the two main things that I was concerned with was the power density and the efficiency of the buck converter. So basically, I found two papers that detailed small form factor lithium ion chargers that didn't include ASIC design. A very popular topic of research right now is lithium ion controllers in ASIC design. So like literally putting it on silicon. So this was the only one that kind of had a distributed non-monolithic charge topology. So to achieve, in these papers, a lot of the authors used gallium nitride transistors, novel switching topologies, as well as zero voltage switching. So these techniques couldn't be employed since the topology was already selected when the buck controller charger was selected, but still, the values used from these papers will be used to benchmark the system. So from paper 1, there was a power density of 0.11 watts per millimeter squared at an efficiency of 98.5%. And for paper 2, there was a very high power density of 0.7 watts per millimeter squared at an efficiency of 86.6%. So we'll see how that stacks up to my later statistics. So getting into the actual component modeling. And so I said system modeling using standard equations because basically the way how this worked was that passive components were selected by setting an operation parameter and then solving the equation for a component value. And then later these were compared in the simulation. And then finally, using a parameter-based search, the components were selected from DigiKey. So as you can see here, these are just the formulas used to select the three main components, which were the input and output capacitors, as well as the inductors, the three main passive components. So this was the selected inductor, has an inductance of 6.8 microhenries, current rating of 10.2 amps, DC resistance of 13.3 milliohms. That was really important since the charge voltage is 8.25 amps, the average charge current once you account for the ripple. An area of 105 millimeters squared, and it's manufactured by TDK Corp. So you can find, those are the part numbers, and you can find it on DigiKey. The other thing to note here, it's not included on the slide, but the selected ripple current was 1.25 amps. So we'll see that later in the simulation. This was the selected capacitor. So the selected output ripple voltage was 20 millivolts, and the selected input ripple current was 4.6 amps, which was kind of high, but that was necessary due to the high duty ratio of the buck converter. So basically, we'll compare that at the end. These were pretty big resistors. As you can see, they're package size 2220 and have a rated voltage of 100 volts. And that was selected because there was a lot of non-ideal characteristics that had to be dealt with due to the parameters of the circuit. So with a switching frequency of 600 kilohertz, the impedance of the inductor was greatly reduced, or of the capacitor. The capacitance of the capacitor was greatly reduced due to the series inductance, as well as the capacitance was derated due to the DC bias current, 24 volts across a large value of 10 microfarads. So that's why this may seem kind of overvalued, but it was due to the non-ideal components or non-ideal characteristics of capacitors. Finally, the active component selection. So basically, this was just done following a figure of merit scoring system that was found on the BQ24610, which is the charge controller data sheet. So as you can see, the equations are over here. So basically, the figures of merit, where it's such a high switching frequency and such a high current, modern day transistors kind of having caught up. So you have to trade off the input capacitance or the Miller capacitance with the conduction losses, or the conduction, the RDS on. So that's what this is doing here, the FOM top, FOM bottom, the figure of merit. And basically lower is better. So the Miller capacitance would be the gate to drain charge, which is basically directly proportional to the input capacitance. And then on the low side FET, the gate charge and the RDS on was considered. And so as you can see here, this kind of resulted in a matrix of all different 4 different capacitors on DigiKey that I selected. And this third one here was actually probably the best selection, but the area of that transistor was literally exponentially bigger than the last one, and the figure of merit scores aren't much in the difference. So I actually selected the bottom FET, the Texas Instruments CSD half bridge IC. So this has the high side and the low side and MOSFETs contained in it, and it's made specifically for high frequency switching buck converters. So as you can see, the input capacitance is really small at 518 picofarads, has a continuous drain current of 15 amps, an area of 9.9 millimeters squared. This is really tiny, and a drain to source voltage of 30 volts. And I also included the part numbers and the DigiKey part numbers down there, just in case if you wanted to take a look. And then finally, with the mathematical analysis, you can see this in the paper. I just did a high level overview here. I calculated the conduction switching losses for the FETs, as well as the copper losses on the inductor, in order to get kind of like a total system power loss. And then I use that to calculate total system efficiency. So as you can see, I calculated a total system loss of 3.47 watts at a system efficiency of 9.83%. And so now just looking at the simulation, so basically this is just going to go through like how I put together the simulation. Then we're going to look at the simulation and the waveforms and the outputs. So I found it really hard. I couldn't find any SPICE models for the charge controller, so I simulated the gate drivers in the charge controller using 2 pulse sources in LTSpice. In the data sheet, it said that I had a 30 nanosecond dead time between the pulses, so that was also programmed into the pulses. And as you can see, the bottom one there has a 24 volt gate drive, so that's for the low side FET. But for the high side FET, the bootstrap circuit straps it up to 48 volts, so that was just inputted into the pulse. These are the passive components. So as I talked about before, there's non-ideal characteristics associated with the inductor, capacitors, as well as I added some sense resistors, which were a part of how the buck controller controls the charge profile. So here I'm just showing that like I inputted, although the capacitors were, I inputted the non-ideal characteristics. So for example, at 24 volts at 600 kilohertz, the selected capacitor would be rated at 8.7 microfarads with a series resistance of 4.35 milliohms. And similarly, something similar for the inductor as well as the sense resistor and the output capacitors. And so this just ensures that we have as close to real world performance as possible. And then finally, for the half bridge gate driver, I downloaded a SPICE model off of the Texas Instruments website and created a symbol and put that into the simulation. And so finally, this is the total simulation. One thing to note here, or 2 things to note here, is that I modeled the source. So we bought a really cheap Chinese 24 volt, 150 watt AC to DC converter. So I expect that this is going to have really bad line voltage or line leakage. So I put a 200 millivolt 60 hertz sine in series with the 24 volts DC to mimic the leaked line voltage. As well, usually lithium-ion cells are modeled as constant current sources in simulations, but that was giving me some really weird transients. So I just used a resistor, so those would be damped away. And then finally, you can see here this .IC. So that was used to initialize all the different nodes at their voltages so that it would start from a steady state since the charge controller handles soft start of the buck circuit. And so here's the inductor ripple. You can see it's 1.5 amps, so it's just a little bit higher than the 1.25 amps. Here's the output ripple voltage. It looks big, but it's literally 17 millivolts. It's super, super tiny. That's the output ripple voltage. Here's the input current ripple. You can see the switching shoot through here on the FET. Can't be avoided, but you can see that the average is around 4.8 amps, which is a little higher than I expected. And here's just a really interesting one. So this is looking at the input power versus the output power. So the green there is the DC source, and the blue is the simulated battery. And so essentially that was used to get end-to-end efficiency. And so here's the results. You can read them in the paper as well. Basically everything pretty much matched up. There was a couple values that were worse, couple values that were better, but they were all within like an accuracy of like less than 10%, which felt pretty good. And then finally, looking at the circuit board layout. So here's a render of the circuit board. So as you can see, this is this is the bottom side of the board. So there's a connector there that goes to a load switch, which turns on. It's controlled by the charge controller, which is here. Goes through the sense resistor that I was talking about before into the input capacitors. Then that goes into the half bridge circuit, which goes into the inductor, through another sense resistor, onto the battery rail, which is right there, as you can see on that power plane. So that's just the PCB layout. So just another note, when I would calculate power density, I'd calculate it as a square from here over to the side of the FET. And so that was a total area of 506 millimeters squared with a total power of 103 watts delivered to the battery at the highest charge power. So yeah, as you can see, 22.2 millimeters by 22.8 millimeters for a total area of 506.2 millimeters squared, giving a total power density of 0.22 watts per millimeter squared. So if you remember from the literature review, that's actually a little bit higher than one of the papers, which was 0.11 watts per millimeter squared, but much less than the 0.7 watts per millimeter squared. And there's just nothing that can be done about that. That was just because I was using CMOS technology versus gallium nitride. And finally, this is a cool little picture that I wanted to include. So this is just looking at the total area, so 22 by 22 millimeters square, drawn on a piece of loose leaf, and comparing it to a Looney or an 18650. So that's actually one of the cells that's going to go into the battery. So that's really tiny. So if you can imagine, the inductor is most of that size with the capacitors and so it's just really small. And a total 103 watts going through that. And so finally, I just want to say, big thank you to the Professor Motion and the TA for such a great semester. I really enjoyed learning about power electronics. It was really interesting. And I just appreciate the cooperation and just how much patience you had when we switched over to online learning. And there's my references. Perfect. So now I'm just going to so there's the simulation, but I also just want to show you, so this is the total system. So this is a render of the total system. So as you can see, the charge connector is this one here. And then I flip it around, and then that's the charger there. And then I also included, so I included the Gerbers, which is the manufacturing files for the PCB, for the total PCB. I included that just as a little bonus. And as well, I included the schematics for the whole battery management system. But if you just want to see the charger, you can open up that page. And that's the schematic there for the charge controller, the buck converter, the bootstrap circuit, as well as all the control circuitry, feedback, instrumentation circuitry. All right, well, thank you very much for listening. I hope you enjoyed. Merry Christmas, Happy Holidays, Happy Kwanzaa. Bye-bye.